So this is not about NLP, this is about image recognition. So I work on a project called iNaturalist at California Academy of Sciences, and our project, the idea is that we are building something like Shazam for nature. So the idea here is that you're out on a hike, you see a lizard or a butterfly, you don't know what it is, you snap a picture of it, we'll ID it for you, we'll teach you about it, and then once we have a consensus about what you've seen, we upload that to a conservation database where researchers can use your sighting as part of a larger data set to answer questions about sort of habitat loss or climate change or any of these things and how they're affecting species. Right now it's all people powered, but that's part of what I'm here to talk about is the advances we've made. So iNaturalist, this project generates a significant portion of the world's biodiversity data. So 93% of all monarch butterfly records in GBIF from the last decade are from iNaturalist. This is an example of the kind of research that can be done with iNat data. So a conservation researcher at Cal Academy was able to establish the relationship between the growth of this particular, growth in sightings of this particular nudibranch with sea surface temperatures in the Bay Area. So basically, as sea surface temperatures in the Bay Area get warmer, we get new wildlife in the Bay Area that we don't normally get. And that can happen because of people going out to the docks and making observations. So we're growing really fast. We're doubling every year. We have 5 million observations right now, but we're currently at a pace to hit 50 million in 2020. And again, this is all people powered. So every one of these observations is getting ID'd by a person, and that can take 2 to 4 days on average. And so we started looking at ways to speed that up, and one of the ways to do that is through deep learning. So we built a data set. We basically built an export of all the photographs that we've got. So this is 5 million images of wildlife, 13,000 species. We also, for those of you who are interested in this stuff, we split our observers by into separate. So an observer can only be in one of training, validation, or test. And this is mainly to make sure that, say, a photographer that's really interested in one species, we don't overlearn their photography characteristics. So we built a pretty straightforward deep learning training pipeline. We're using TensorFlow. We're using Inception v3. We've got a couple donated GPUs. We do some pretty basic stuff like, we do random crops and flips and color transformations and stuff. A lot of this, all this is open source, by the way, so there will be links at the end. And then our prediction layer is also pretty straightforward. So we're running, a Flask container. We're running that same TensorFlow Inception v3 model that we built. We're running on a super commodity, super cheap cloud hardware. It's just fine. And we mash that up with, this is a map of, parts of Texas and Mexico where a particular frog is seen. So we know, we have a lot of geospatial data about where observations could be seen. So we don't just know what you saw based on what it looks like, but also based on what could be seen in that area that you are. And then similarly, we can look up in the tree of life. So we may not know what kind of lady beetle it is, but we know that it's a lady beetle and not a bee or any other kind of insect. We just deployed this into the iOS App Store last month. The link is here, and so you can see, as you make an observation of nature, you'll get a parent class, you'll get a genus in this case, and you get a list of species to choose from. Some brief accuracy results. I mean, the main takeaway from this graph on the left is that as the number of training images for a species label grows, we get more accurate. So our main priority here is to get more images. So we need more people using the apps. So there's this sort of virtuous cycle that happens as the app gets better with this deep learning stuff. The other interesting thing here is that when we don't calculate a common ancestor all the time, but when we do, we're right about it 93% of the time, which is pretty cool. So some future challenges that we're looking at. The first of them is this up here on the left. We're interested in hierarchical ontologies. So this has been part of ImageNet since the beginning, the idea that seven-spotted lady beetle is also a lady beetle, which is also an insect. Most people haven't been doing a ton of research on this, but this is sort of how human knowledge works, and so it would be really great if more deep learning projects could take advantage of this. This down here on the bottom left, this is a camera trap. You might set this up in your backyard and use it to record, on a motion sensor and record photos of things or videos of things that have walked through your backyard. So we're interested in doing deep learning on that kind of stuff. Here in the top right, this is a Skinner teaching machine, I think from the 1930s. We're interested in the idea that once the neural networks get smart enough about what these things are, can we use that knowledge to train humans to make identifications better too? Can we train kids better on conservation or on biology or on natural history? And finally, we're certainly seeing throughout the research in computer vision that larger images really make a difference. And so, so that's it.